So we are going to move to session 3.6. Okay, that is about row space and the column space, and in fact, this is the one of the most important part of linear algebra. So, if A is an n by n matrix, then the n vectors in n-dimensional space corresponding to the rows of A, and is referred to as the row vectors of A. Okay, so when we talk about this, we can draw a matrix like here. So the matrix A is m by n. That means we have m row vectors. We have n column vectors. And for each row vector, it's in n-dimensional space. And each column vector is in m-dimensional space, right? So the row vectors of A is n-dimensional. And the n vectors in m-dimensional corresponding to the columns of A, that is referred to the column vectors of A. So here vertically we see the column vectors. Horizontally we see row vectors, right? Okay. So now if A is an n by n matrix, the subspace of R1 by n spanned by the row vectors of A is called the row space of A. So again, we draw the matrix A. Now, the vector space spanned by the row vectors of A is called the row space of A. Okay? On the other hand, for the vector space spanned by the column vectors of A is called the column space of A. Okay? Right? Because row vectors, the set of row vectors would span a vector space. And the column vectors would also span a space. One is row space and one is column space. Okay, and this is called 列空间. This is called 行空间. 行空间跟列空间，行就是直的叫行嘛，这一行一行一行，横的呢叫一列一列，这一列一列一列一列一列。好，所以一个叫列空间，一个叫行空间。Okay, row space and column space. So now let us see some example. If A is looking like this, which is a 2 by 3 matrix, and the row space of A, that means the space spanned by the row vector. So here, A1 is the first row vector. A2 is the second row vector, right? And the space, the row space of A can be represented as 1, 0, 0, this row vector, and 0, 1, 0, this is the second row vector. It can be represented, any vectors in the row space of A can be represented as a linear combination of these two row vectors. So assume the coordinate of these two row vectors are alpha and beta. So when we add them together, we get alpha, beta, 0, right? Because this is alpha. The first entry would be alpha. The second entry would be beta. And the third entry would be 0. So the row space of A can be represented as this alpha, beta, 0, where alpha and beta can be arbitrary real numbers. Okay, alpha, beta, 0. And in fact, if you look at this carefully, geometrically alpha, beta, 0 represent a two-dimensional subspace in a three-dimensional space. And in fact, it's a plane, right? It's a plane in a three-dimensional space, right? Okay, so all vectors on the plane, and this plane, all the space, just like this, okay? So all the vectors on the plane, where the third entry is 0, any vectors on the plane can be represented as a linear combination of 1, 0, 0 and 0, 1, 0. So the row space of A is a plane in a three-dimensional space in this case, right? And the column space of A would be linear combination of 1, 0, 0, 1 and 0, 0. So remember that the dimension of the column vectors of A is 2. The dimension of the row vectors of A is 3, right? So this is 2 entries here, 3 entries here. Okay, so the column space of A can be represented like this, which is alpha beta. And in fact, alpha beta is the entire R2 space. Okay. Okay. So let's talk about theory 3.6.1. Two row equivalent matrices have the same row space. So do you remember what is row equivalent matrix? That means when we do a series of reduced row operation, we can make two matrices together the same. We can reduce the matrix to the same matrix. That is called row equivalent matrix, right? So here two row equivalent matrices have the same row space. How can we prove that? So if B, the matrix B is row equivalent to A, then B can be formed from A by a finite sequence of row operations, right? We already know that. Thus, the row vectors of B must be linear combination of the row vectors of A, right? Consequently, the row space of B must be a subspace of the row space of A, because the row vectors of B must be linear combination of the row vectors of A. Therefore, row space of B must be a subspace of the row space of A. And on the contrary, A is row equivalent to B. Therefore, for the same reason, the row space of A is a subspace of the row space of B. Therefore, the row space of A should be equal to the row space of B. OK？ 好，这个部分听起来有点像绕口令，好，但应该很简单啦。好，就是说，因为 B 这个矩阵里面的 row vector 都可以表达成 A 这个矩阵的 row vector 的线性组合，所以说呢 ，B 的列空间一定会是 A 的列空间的子空间。反过来讲 ，A 的列空间也一定会是矩阵 B 的列空间的子空间，因此互为子空间，因此这两个空间一定是同一个空间，这样子。OK， 好，那讲到 vector space 的时候哈，其实在线性代数里面，这是属于比较抽象的，好，讲到什么航空间啊、列空间的时候，就是大家需要一点想象力，这边比较抽象一点。OK， 好 ，OK。And now we introduce another term that is called rank. Okay, what is rank? The rank of a matrix A is the dimension of the row space of A. The dimension of the row space of A is called rank. Rank. Okay. And in the previous example, example number 1, rank A is equal to 2. Here, yeah, because here, the row space, the dimension of the row space is 2, because we can use 2 row vector to span the row space of A. Therefore, the dimension of the row space of A is 2. Therefore, the rank of the matrix A is 2. Okay? Okay. And to determine the rank of a matrix, we can reduce the matrix to row echelon form. Okay? Then non-zero rows of the row echelon form will form a basis for the row space. So if you understand this well, it should be easy, right? Because we can use a series of we can use a series of row operation to reduce a matrix into row echelon form. And after doing that, some row vectors would be all equal to 0. So what does that mean? That means this kinds of row vector can be represented as a linear combination of other row vectors, right? So the other non-zero rows can form the basis of the row space. So the numbers of non-zero rows is the rank of the matrix A. OK， 好，这边用中文再讲一次，就是说我们要去决定一个 matrix 的 rank 的时候，好，这个 rank 这个字呢，如果翻成中文，很奇怪，叫做什么字啊？啊，念就变成这个字，好，这个 rank 这个变成这个字，啊，这个字念成字，好，那不管了，没有人念成中文的啦，好，反正我们都讲 rank， 好，一个矩阵的 rank 可以怎么找呢？我们就是去把这个矩阵 A 去做一系列的列运算，然后呢，看做完之后，最后剩下多少个非零的列，而这些非零的列，其实事实上就是构成了列空间的基底的数量，就是形成列空间的基底啦。好，那我们就看说，那么有几个非零的列，那它就是我们的 rank。好，那为什么是这样？因为那些会被消除变成零的那些 row 那些列向量，代表说它可以表达成这些非零的 row vector 的线性组合，代表它没什么用啦。啊，所以还记得我们之前讲过说，怎么样可以形成基底？基底必须是线性独立嘛，对不对？好，那如果说，比如说我们随机的在一个三维的空间当中拿4个向量出来，它一定是线性相关，因为一定至少会有一个人可以表达成其他3个人的线性组合，对不对？好，那个人就是属于没有用的人，没有用的 vector。好，这个都跟之前讲的东西都互通的哦。好，那所以这边呢，事实上，这个 rank 也就是那些 linearly independent 的向量的数量，就是 rank。Okay? Okay, so let's see another example. So originally, the matrix A is looking like this. And we can do a sequence of row operation to reduce A into U. And now we see that the third row becomes all 0. Therefore, 1, -2, 3, and 0, 1, 5 will form a basis for the row space of U. And the rank of A is equal to the rank of U is equal to 2, because now we have 2 non-zero rows. The rank is 2. Okay? Okay, and now we consider the linear system AX equals to B. It can be written as a matrix form looking like this. Here is the matrix A, here is the column X, no, here is the vector x, and here is the vector b. And then remember that when we write down Ax equals to b, actually it can separate as S1 times the first column vector plus S2 times the second column vector, and so on. That would be equal to B1 to B2 to Bm, right? And remember that this is the first column vector of A, this is the second column vectors of A, and this is the n column vectors of A. And in previous sections, we said that this linear system is consistent, or this linear system has solution as long as the vector b can be written as a linear combination of the column vectors. Remember that? And now we know that the linear combination of column vector, what does that mean? That means the column space of A. So the left-hand side, the meaning of the left-hand side is the column space of A. So by combining these few statements, we can say that Ax equals to b is consistent if and only if the vector b is in the column space of A. This statement is extremely important in linear algebra. Okay? So let me turn to Chinese again. 好，之前我们就讲过说，一个线性系统 AS 等于 B。事实上，等号左边它的意义其实就是我们用 x1、x2 一直到 xn 来当系数，我们去对 A 这个矩阵的行向量做线性组合嘛，对不对？就是 S1A1、S2 加上 S2A2 一直加到 SNAN， 它等于是等号右边的 B1、B2 的 Bm。那我们之前就讲过说，什么时候这个线性系统会有解？就是说 B1、B2 到 Bm 这个向量可以表达成矩阵 A 它的行向量的线性组合嘛，对不对？我们是不是讲过这句话？好，那我们现在又知道了矩阵 A 的行向量的线性组合是什么意思呢？它的意思就是矩阵 A 的行空间的意思 ，column space。所以整合以上这些话的意思就是说，这个线性系统 AS 等于 B 会有解 ，is consistent， 它有解，什么时候有解呢？如果 B 这个向量是在 A 的行空间里面的话，或者你换句话说，如果 B 这个向量可以写成 A 的行向量的线性组合的话，那么这个线性系统就有解。好，这样可以吗？好，这个是线性代数里面极为核心的一个观念哦。好，非常非常核心的一个观念。好 ，OK， so theorem 3.6.2. A linear system AS equals to B is consistent if and only if B is in the column space of A. Okay, so this theorem is extremely important in linear algebra. Okay, so now let's look at a special case. If the vector B is equal to zero vector, then the linear system AS equal to B becomes AX equals to 0, right? And you can write it down as S1A1 plus S2A2 plus SNAN equals to 0 vector. And this equation looks quite familiar, right? Remember that when we want to check whether A1, A2, and AN are linearly independent or not, we write this equation down. And to check whether this equation has only the trivial solution. Remember that? Okay, so right now, if the linear system, the right hand side is equal to 0 vector, then we can write this equation down. And it represents AS equal to 0. And this homogeneous system have only the trivial solution if and only if what? If and only if A1, A2 to AN are linearly independent. We already know that, right? So if and only if the column vectors of A are linearly independent. If they are linearly independent, then AS equals to 0 has only the trivial solution. The so-called trivial solution is that we set all x, x1, x2 to Sn as 0. This would be, we always have the trivial solution for this kinds of system, right? And now, we have theorem 3.6.3. Okay. If A is an M by M matrix, the linear system AS equals to B is consistent for every vector B in Rm. If and only if the column vectors of A span Rm. Okay, so again, we draw the matrix A, which is M by N. So now the column vectors of A1, A2 to AN, AI is in Rm because it is M dimensional, right? So if the column vectors of A span Rm, how can it span Rm? How can they span Rm? That means A1, A2 to AN, A1, A2 to AN can span Rm because part of them, for example, M of these N vectors are linearly independent. So if these N column vectors can span Rm, that means any vector, any M dimensional vector can be in the column space of A. Right? Okay. I'm not sure whether, okay, we have a proof here. Okay, here. AX equals to B is consistent if and only if B is in the column space of A, right? Sure. It follows that AS equals to B will be consistent for every B if and only if the column vectors of A span Rm. Right? 好，如果 A 的 column vector 能够展开整个 Rm 这个空间，那 B 这个向量当然是在 Rm 这个空间里面的啦，那就代表说 B 这个向量可以被表达成 A 的 column vector 的线性组合嘛，那当然这个就会有解啦。啊，这个就是第一个证明 ，OK？ Okay, the second statement. The system AS equals to B has at most one solution. At most one solution for every B in Rm, if and only if the column vectors of A are linearly independent. The column vectors of A are linearly independent. Okay, so if the column vectors of A are linearly independent, that means it can span Rm. Okay, and because they are linearly independent, the way to represent the vector B would be unique. Remember that? Remember that? Okay? So if a set of linearly independent vectors, we use a set of linearly independent vectors to represent a linear combination, then these kinds of linear combination would be unique. 还记得这件事情吗？如果这一堆向量是线性组合，我们现在把某一个向量表达成这堆线性组合的向量的，再讲一次，我们把某一个向量表达成这堆线性独立的线性组合的话，这个组合法是唯一的。我们之前讲过这件事。OK。We can also show the proof. The proof is a little bit long. Okay. If A s equals to B has at most one solution for every vector B, then in particular, A s equals to 0 can have only the trivial solution. Sure. If A s equal to 0 have only trivial solution, then the column vectors of A must be linearly independent. Yeah, just as we mentioned here. Not here. Here. Okay? As we mentioned here. So we just use a special case to prove the one direction. And conversely, if the column vectors of A are linearly independent, AS equals to 0 has only the trivial solution. Okay? And if x1 and x2 are both solutions of AS equal to B, then S1 minus S2 would be the solution of AS equals to 0. That means S1 minus S2 must be 0 vector. Therefore, x1 must be equal to x2. So this is we are going to say that we have only one unique solution. In fact, x1 is equal to x2. Okay, so this is the theorem 3.6.3. Okay. So now if A is an n by n matrix, if the n column vector of A span Rm, again, we draw legs. Matrix A, m by n. Now we have n column vector, right? And each column vector is m dimensional. If the n column vectors span Rm, then n must be larger, equal or larger than m. Why? Because no set of fewer than m vectors would span Rm. Right? Just as we say that to span a three-dimensional space R3, we need exactly 3 linearly independent vectors. If we just pick 2 three-dimensional vectors, we are not able to span R3. Remember that? Okay? 好，所以呢 ，A 现在 A 我们现在矩阵 A 我总共有 n 个 m 维的 column vector。好，我有 n 个 m 维的 column vector。那而且呢，这 n 个 column vector 它能够展开 Rm， 如果它可以展开 Rm 的话，那么我的 n 呢一定大于等于 m。为什么呢？因为你 n 不可能小于 m， 你小于 m 的集合，你不可能展开出 Rm 的。就如同说，我们如果只取2个3维的向量，我们不可能展开出整个3维空间。我们要展开3维空间，我们一定至少要有3个向量，而且这3个要刚好线性独立。所以我取出3个向量 取出三个三维空间的重讲，我取出三个三维的向量，我可能可以展开出整个三维空间，如果它们线性独立的话。OK， 那我如果取出四个三维的向量，我比较有可能可以展开出三维的空间。我取出五个，也有可能是展开出三维的空间。只要这五个里面其中有三个它是线性独立的，那么我就可以展开出这个三维空间。OK， 好，如果你听不懂我在讲什么的话，代表说你前面的东西你要复习了，好，就是你还没有融会贯通。好，那很不好意思，这个线性代数呢就都是这样，它完全就是你前面没有懂，那它全部都是连贯的，啊，全部都连贯的，所以一定要跟上这个进度。好 ，OK， so this is the first statement. The second statement, if the n columns of A are linearly independent, then n must be equal or smaller than m. Why? Because every set of more than m vector is linearly dependent. Just as we say that for three-dimensional vectors must be linearly dependent, right? For three-dimensional vectors must be linearly dependent. There must be at least one vector that can be represented as a linear combination of others. Okay, so in this case, n must be smaller or equal to m. So for example, two three-dimensional vectors, it could be linearly independent. So if the n columns of A are linearly independent, then n must be smaller or equal to m. Okay? So finally, if the column vectors of A form a basis for Rn, what does that mean? That means the column vectors of A are linearly independent and they span Rn. That means we need to combine these two statements. So the first statement says that n should be larger or equal to m. The second statement means n should be smaller or equal to m. So if we combine these two statements, that means n should be equal to m. So if the column vectors of A form a basis for Rm, then n must be equal to m. That means A is a square matrix. Okay? Okay. So an n by n matrix A is non-singular if and only if the column vectors of A forms a basis for Rn. So as we said that this is a square matrix, and if the column vectors of A can form a basis, that means the column vectors should be linearly independent. And we have mentioned that as long as the column vectors of A are linearly independent, then the matrix A must be invertible, must be non-singular. Okay, it can be easily proved, right? Since A is non-singular, then all columns of A are linearly independent. And these n column vectors form a basis for Rn. Okay. Okay. So it really takes time for you to realize or to understand the meaning of column space and row space. Okay. You need more practice. Okay. So now we introduce another term called nullity. The dimension of null space of a matrix is called the nullity. So remember what is null space? That is AS equals to 0, right? The all vectors of X form the null space. That is called the matrix A's null space. All possible solutions of this linear system forms the null space of the matrix A. Okay? And then we just write down as n of A. And the dimension of the null space is called nullity. Nullity. Okay. So if A is an n by n matrix, then the rank of A plus the nullity of A would equal to n. This is called the rank nullity theorem. Okay, so how can we prove that? Let A be the row echelon form of A. Okay, and remember that the rank of A means the numbers of non-zero rows, right? The numbers of non-zero rows in U is called the rank of A, right? So here we denote it as R. So R means we have R leading variables. We have R non-zero rows in U, as well as we have R non-zero rows in U. And then what is the nullity of A? Nullity of A is actually the numbers of free variables. So when you try to solve A as equal to 0, remember that when you try to solve this linear system, we would find the numbers of free variables. And the numbers of free variables is actually n minus r. Therefore, the rank of A plus nullity of A would be r plus n minus r. That would be equal to n. Okay, let's see some example. For example, here, the matrix A is a 3 by 4 matrix. Okay, find a basis for the row space of A and a basis for the null space of A. Okay, and verify the dimension of the null space is n minus r. So how can we do that? First, we just do row operation to reduce A into the reduced row echelon form. So reduce from A to U, it becomes this, the matrix. And we see we have two leading variable, this variable and this variable, and we have two non-zero row vectors, right? Therefore, 1, 2, 0, 3, 0, 0, 1, 2 form a basis for the row space of A, and therefore the rank of A is equal to 2 because we have two non-zero rows. Okay. And now when we try to solve AX equal to 0, we can use this reduced row echelon form to solve this linear system, right? So we just write down 1x1 plus 2x2 plus 3x4 equal to 0. 1x3 plus 2x4 equals to 0, right? Just like this. Okay, and then we can write down the general solution of this linear system. That is, we can set x2 as alpha, x4 as beta, because x2 and x4 are free variables. They can be set arbitrarily. And x1 is equal to negative 2 alpha minus 3 beta, alpha, negative 2 beta, and beta. And this general solution can be written as alpha times this vector plus beta times this vector. Okay, and the negative 2, 1, 0, 0, and the negative 3, 0, negative 2, 1 forms a basis for the null space of A. And because we use and because the basis has two vectors, therefore the dimension of the null space is 2, which is n minus r, 4 minus 2, that is 2, right? So let me explain this in Chinese, okay? 好，我们现在这里要算的是这是一个3乘4的矩阵。好，首先呢，你要找到它的行空间的基底。那怎么找行空间的基底呢 ？row space 的基底，那其实你就是做一系列的基本列运算嘛，把它变成是这种精简的形式。那你就去看说这个精简的形式里面，非零的 row 有几个啊？有2个，所以它的 rank 就等于2嘛。好，那我们现在呢要来解 AS 等于0，那我们要找出所有可能的 x。那这件事情我们早就会做啦。好，我们呢做完这个基本列运算之后，我们就可以利用这个 u 好去写下这个，把这个线性系统呢，把它简化成这样子的线性系统。我现在的这个红色的是这个线性系统。好，那这个线性系统它的通解就长这样啊，阿尔法乘上这一个加上贝塔乘上这一个，也就是说，所有让你从 AS 会变成0的这些 x 都符合这个形式嘛。好，所以我的 null space 其实就是这个就是我的 null space， 而这个 null space 的基底呢，就这2个啊。好，所以我这个 null space 的基底有2个向量，因此我这个 null space 的维度就等于2嘛。好，那 null space 的维度是2，row space 的维度也是2，或者是 rank 也是2，那2加2的就等于4嘛。那4是什么？4其实就是你有4个 column vector 嘛，这是一个3乘4的矩阵嘛。OK， 好，2加2等于4，他在讲这件事情。好 ，OK，so about the column space. Okay. The matrix A and U in example 3 have different column space. However, their column vectors satisfy the same dependency relation. Okay. Example 3, when we mention the column space of A and the column space of U, when we mention the column space of U, we have the basis that is 1, 0, 0 and 0, 1, 0. Why? Because this is the leading variable. This is the leading variable. We can use these two column vector to form the column space of U. And for the matrix A, we can also use the first column vector and the third column vector to form the column space of A. Okay? And the column space of A and U are different. You can see that the column space of U, the basis is 1, 0, 0 and 0, 1, 0. You can see that the column space of U should be a plane in a 3-dimensional space, right? However, if we take the first column vector and the third column vector of A, we have 1, 2, 1 and negative 1, negative 3, 1. These two vectors are linearly independent, and it can also form a plane in a 3-dimensional space. However, this plane may be different from this plane. So the column space of A and U are different. However, their column vector satisfy the same dependency relation. For example, U2 is 2U1, U4 is 3U1 plus 2U3. And we can also write down A2 is equal to 2A1. Here, 2 for 2 is equal to 2 times 1 to 1, right? And A4 can be written as 3A1 plus 2A3, right? So the dependency relation are the same. Okay. So in general, if A is an m by n matrix and U is the row echelon form of A, and since AS equals to 0, if and only if US equals to 0, their column vectors satisfy the same dependency relations. Okay, just as we mentioned in the previous slides. Okay. So now theory 3.6.6. If A is an m by n matrix, the dimension of the row space of A equals to the dimension of the column space of A. Okay, so we have mentioned that the dimension of the row space of A is called the rank of A. And actually, the dimension of the column space of A is also the rank of A. Okay? So why? To find the column space of A, we can use the row echelon form U by determining the columns of U that corresponding to the leading one. Yeah. To find the column space of A, we just take the columns that corresponds to the leading one. These same columns of A will be linearly independent and forms a basis for the column space of A. So actually, I have done this before. So as I mentioned here, because the leading variable is at the first column and the third column, so we can just take the first column of A and the third column of A to form the basis of the column space of A. Okay. Okay, so these same columns of A will be linearly independent and form a basis for the column space of A. So in this case, we know that because the leading variable, the numbers of leading variable of U will be equal to the numbers of column vectors that form the basis of the column space of A. Therefore, the rank of A, the numbers of non-zero rows, that is the rank of A, is equal to the numbers of column vectors that forms the basis. OK， 用中文讲一次，讲得很绕口。就是说呢，当我要去找一个矩阵 A 它的 column space 的基底的时候，我可以使用什么呢？我可以使用我经过这个转换之后的这个 row echelon form U， 我去看它对应到 leading variable 的 column 是谁。像这个例子来讲，它 leading variable 对应到的 column 是第一个 column 跟第三个 column， 对不对？好，那我就直接拿 A 这个矩阵的第一个 column 跟第三个 column 来当成是 A 的 column space 的基底。OK， 好，那U 呢 ？U 这边我们看到的 leading variable， 像这个有两个嘛，它在第一列跟第二列，所以说呢 ，U 的 rank 就等于2，A 的 rank 也等于2。好，那我们刚刚就又讲说，我们是如何去选出 A 的 column space 的基底的呢？我们又是去看这个 leading variable， 那不就都一样吗？所以说呢 ，A 的 column space， 它的 column 拿来当基底的 column vector 也一定就是两个啊。 一定就两个，因为我们是去看它的 leading variable 的位置，它有两个 leading variable，那你就是会挑到两个这个 column vector。好，所以说 column space 的基底一定就是两个。OK， 好，所以我们讲说，矩阵 A 的 rank 其实就是它的 row space 的 basis 数量，也是它的 column space 的 basis 数量。好 ，OK。So let's see some example. Okay, so the matrix A is a 4 by 5, 4 by 5 matrix. Okay, and we can do a row operation to reduce A from A to U. Okay, and after doing that, we see that we have three leading variable, x1, x2, and x5. And yeah, the corresponding column vectors, the first, the second, and the fifth column vectors form a basis for the column space of A. Therefore, the rank of A is equal to 3. Okay, the dimension of the column space is also equal to 3. So in this case, we know that the rank of the matrix A is actually the dimension of the column space of A, and also the dimension of the row space of A, right? So the last example, find the dimension of the subspace of R4 spanned by these four vectors. Okay, and then we can just combine them as a matrix, as here, S1, S2, S3, S4, and then we do row operations to reduce X into this. So finally, we get two leading variables only, right? So the leading variables are x1 and x2. Therefore, the rank of X is 2. And x1 and x2, the first and the second column vector, form the basis of the column space of X. Therefore, the dimension of the span of S1 to S4 is 2. Okay? Yeah. So this is the end of the chapter 3. Okay, chapter 3 is long. It's a very long chapter. Any question about this part? (有没有什么问题？好，没有的话 if you don't have no question, you don't have no, yeah, you don't have question, let's take a minute for, let's take a break for 10 minutes, okay?